So when we're looking at it physically, air is considered a fluid. So air resistance is fluid friction. Now, which is greater, the fluid friction of air or the fluid friction of water?
Water.
Water is greater fluid friction than air. Good.
More dense.
Okay. Now, Ms. Steele was talking about terminal velocity before. Terminal velocity is simply, what does it mean? That's the velocity at which you die, hence the terminal. What does it mean?
When you stop accelerating.
When you stop accelerating, you're not going to go any faster. Terminal velocity is the fastest you're going to fall. So let's take a look at Newton's second law of motion. So Newton's first law of motion talks about, what's Newton's first law? You guys learned this back in kindergarten, maybe?
Third grade.
Third grade again. Okay.
First grade, my bad.
First grade.
So remember Miss Sandy the bucket.
Ah, that's a good one, actually. So Newton's first law, what is that? I mentioned it earlier.
That's the second one.
Okay, it's summed up in the word inertia.
Oh yeah.
So inertia is what? Okay, so an object in motion will stay in motion. An object at rest will stay at rest unless outside force. Okay? An object in motion will stay in motion, an object at rest will stay at rest unless acted upon an outside force. Now, inertia depends entirely on the mass of an object. The more mass an object has, the more inertia it has. I.e., the harder it is to stop it once it's moving, the harder it is to start it moving in the first place. So, if you were to take a look at a jet airplane and a sports car, they're both on the runway. The airplane is coming up to speed. It's going about 200 miles an hour down the runway. The car, sports car, is going 200 miles an hour down the runway. Now, one of them is going to take off, one of them is not. But the question is, which one has more inertia? Yes?
The airplane?
The airplane has more mass. And what about this? What if you have the airplane on the runway, but just sitting there because the weather's not good? They're waiting for the weather to clear. And the car is going and going down the runway at 200 miles an hour. Now, Mr. Taylor, which one of those two has more inertia?
Well, it'd be the car, because the plane still the plane.
Mr. Taylor, you fell into my trap. Thank you very much. It's still the plane because it depends on mass. We don't need velocity for inertia.
I thought you needed energy.
I still use what inertia is.
Inertia is the tendency to stay in motion or stay at rest. Or you could say it's going to stay what it's been doing. It's going to keep doing what it's been doing. So if it's moving, it's going to stay moving. If it's not moving, it's not going to move. Yeah. Yeah. So that's one of the reasons why it's hard to tackle Andrew Luck. Because he's a big boy. Right? For a quarterback, he's a big guy. It's hard to tackle him. Because he's got a lot of mass for a quarterback. Right? He's able to juke and move a little bit. He's still young. But, where it's a lot easier to tackle indigent. Because he doesn't have as much mass as Andrew Luck. Break when you're back.
That's why I don't play football.
That's why he doesn't play football. Okay.
Oh yeah. Problem 3 on the canoe.
The canoeing one is
All right. Second law of motion.
It was one that angle that you would go across.
Okay. Hey guys. Newton's second law of motion can be written this way: force equals mass times acceleration, or you could say that acceleration equals force divided by mass. In order to accelerate an object, it is dependent on the ratio of its force that you're using to accelerate it to its mass. Now, we've talked about acceleration before, haven't we?
Yeah.
Okay. And since mass is kilograms and acceleration is meters per second squared, that's where we get the kilogram meters per second squared. Or we could say that is measured in newtons. All Alright, let's go backwards for just a second. In the beginning, we mentioned that distance is measured in meters, right? And if we want to know how quickly we change that distance, we find the rate involved. Some people call it rate, some people call it speed, right? And so we say it's meters per second, right? And if we want to find out how fast that rate of motion is changing, then we look at acceleration.
Final velocity.
And so that's meters per second, or meters per second squared, right? And then we're going to throw mass into it. If we're going to accelerate an object that has a certain mass, we want to know how much force it involves. And so we find that force involves kilograms, and we're going to accelerate it, so it's meters per second over second. Right? Or you could more properly write it, I think, kilograms over 1 times meters over seconds over seconds. Or, I think we wrote it before, kilogram meters over second squared, which is also known as a Newton. Now, just a couple weeks ago, I said, get it at the foundation. Hey, ladies in the back, if you can handle it, then we won't allow it. So, we start with distance and speed and acceleration, right? That was our first chapter. I said it's just going to keep building on what we already know. And we're going to add one more unit to it. And there's your Newton. So, the question is, when you go backwards to Newton's second law, his question was, how much force does it take to accelerate a certain mass? And we're going to measure that force, we're going to call that Newton. How we measure it, it's just simply going to be kilograms and acceleration, and we're going to call that whole thing a Newton.
So the formula for Newton is kg multiplied
By meters over second squared. Because it's just, and it makes sense too, because you're like, okay, well, it's the mass, here's my mass, and acceleration, and here's my acceleration. We've already learned those. We're just combining those two. Right? Okay. So, let's take a quick look at this. If we find that F equals ma, or you could say that A equals F over m, or you could say that m equals what? F over A? Right? Let's say Mr. Wright and Mr. Taylor are both pushing on Mr. Schuth down the aisle so that Mr. Schuth can get his Best Teacher of the Year award. They're both using a force of 100 newtons to propel him down toward the stage. Right? Right? Okay. Now, which one of them is going to accelerate Mr. Schuth more?
Clay. Stronger. Clay weighs more. One with the greater mass. Clay has bigger inertia.
Okay. Well, what's the force acting on? On me. Right? And how much force was Mr. Wright using?
50.
100 newtons. And how much Taylor? 100 newtons. So which one is accelerating Mr. Schuth more?
They're the same.
It's the same, right? Because their force is acting on me. I'm the object. Isn't that interesting?
So then technically you would weigh 200 kgs?
No, I didn't say what the acceleration was. So, in order to figure that out, you'd say, okay, well, we want to know what the acceleration is. We would use this part. And we know the force was, so E equals F over m. So we know the force was 200 newtons. What do we still need to know?
The mass.
The mass. Right? So let's see. There's 2.2 pounds per kilogram. So let's say 85 kilograms.
That's 180. No, that's 190 pounds. Yeah.
190 pounds? Oh, that's
185 pounds, I think.
185? That's about right with my clothes on. Okay. So there we go.
That's about how much it is.
So here's the question. If we take 200 newtons divided by 85 kilograms, what happens to our units?
Newtons over
It's newtons over kilogram. So newtons, remember, what's a newton look like? It looks like kilogram times meters per second squared all over kilograms. What factors out? Kilograms. And you're left with? Meters per second squared, which is the unit for acceleration. And that makes sense. That make sense?
Yes.
Okay. And that's how you do it.
Yes.
Yeah, that's so what would be?
Oh.
You just take 200 divided by 85.
Man, that's because you're
I know that.
special.
What is it? You know?
You'd have to get a calculator.
Yeah. You just got here and it already makes sense.
Good. Okay, at 10 minutes. Okay, turn to page 368. 368, this is where most people fall down, is when looking at weight. And that wasn't meant to be funny, but weight is gravity's effect on a certain mass. Most people would say when you say your weight, so Mr. Schuth just mentioned that he had a mass of 85 kilograms. Most people would say that he weighed, as Sokar said, 185 pounds. Well, that's not Mr. Schuth's weight, that's Mr. Schuth's mass. So, weight is just simply mass of the object times the acceleration due to gravity. So weight is a specific example of F equals ma. Therefore, weight is measured in what unit? Yes, newtons, exactly. So weight is measured in newtons. Mass is measured in kilograms or pounds. So most people, they step on the scale and they say they are weighing themselves. However, they are, in a sense, weighing themselves, but the numbers they come back with are not the weight numbers, they're the mass numbers. So what the scale is doing is taking your weight and converting it to mass for you. You're changing it to a different type of reading. So, a lot of times, when you hear me say use your balance, I'm saying, well, mass that object, not weigh the object. Because I want you to report it in grams or kilograms, not newtons. So, weight, in physics, this is another one. It's just one of those terms you've used all the time that's been abused in a sense. Weight is not in kilograms or pounds. Weight is measured in newtons. And it's just mass times acceleration due to gravity, which we all know and love. And what is acceleration due to gravity?
9.81 meters per second squared.
9.8 meters per second squared. We're just going to leave it at 9.1. Okay? I'm sorry, 9.8. 9.81 you can do in high school, and then you can go beyond that when you go to college. Yep.
Isn't that why you would way more if you stand on Jupiter? But
Yes. Because acceleration due to gravity on Jupiter is greater. All right. See you guys.
Oh, here, keep it.